look at some of the examples. Here we're trying to remove 16. So we go to the 20, we compare 20 with 16. 16 is less than 20, so I go here. And then we compare 16 with 10. 16 is bigger than 10, so we go to the right. And now I find the element that I'm trying. Sorry, it says the binary search 3, 2, 3, 20. So we're going to treat the 20. I'm sorry. We try to treat the root, right? And the root does have left children. So that means this is the case too. So based on the algorithm that we have to go to the left child, which is 10. And then we have to look into the most right. So we're searching for the most right. And just obviously, just looking at it, you can see that 16 is the right most children in the left side of this subtree. So in the left side of our subtree, we only have 16 and 14. So, 16 is the largest spot, and that's right most. So we're going to take this up, and we're going to tell the 10 dot right to point to the 16 dot left. So that way we're not losing 14. And then we're going to tell the root that you're going to be 60. So we're swapping it. Another example, we're trying to remove George again, which is our root. It does have a left children, so that's going to be the case 2. We go to the Adam, which is the left child. We're looking to the right of it now. We're finding the most right. So only have one right children, and that's Daniel. So we're going to basically put Daniel on the top, so Daniel becomes the root. And we remove the George. Another example, now we're trying to remove Adam. Adam is the leaf. It doesn't have any children, so that's case 1. And so in order to remove it, we just have to remove it. We don't have to do anything else. And next is going to be the Michael. So we're trying to remove Michael, and so we have to look into this to see if it's a left child or the right child. Sorry, it does have a left child or not. It does have a left child, right, Jones? And so that means that's going to be the case 2. So I need to go to Jones, and then I have to look into the most right. Since the Jones doesn't have any right children, Jones itself is the most right. So we're going to put Jones on the top of Mike instead of Michael, and Michael is going to be removed from the list. So as you can see, even for removing, we only had to do comparison based on the height of that basically subtree. Maximum of number of comparison that we have to do is not going to go over the height of the tree. So that means that it's still going to stay in the log n situation, which is or h, right, the height of the tree. But if our tree is like what we left out here, it's our tree has become like a linked list, then if I want to remove something, then I have to go one by one and do that. That means it's no longer is going to act like a binary search tree. Is going to act like a linked list, which is going to take us order of n. So again, the binary search tree overall performance can be order of log n in the best and average cases if we have random data and the data are not sorted. But if the data is sorted and the height of the tree is equal to or is in order of n, then all these adding, insertion, deletion, complexity, they're all going to go up and they become order of n. But in average cases, when they're listed or the element that we store are in the binary search tree are completely random data, the distribution of the random data is most likely going to be a normal distribution. So that means we're going to have a more balanced tree than like a list, really. So our height of our tree is no longer going to be very in order of n or close to n number of elements. So that way it's definitely going to act as a log n, not really order of n. So it's going to be faster than order of n. Okay, so now we're going to go ahead and write code for it. So I'm going to just use the same video. I'm not going to post another video for writing code. We'll jump back to our code. and we'll start writing it based on all of these analysis that we did. Okay, I'm just going to switch to my Eclipse, and we're going to write the code for deleting. We already did the search. So by the way, if you look at the assignment, I asked you guys to complete the BFS and also implement the DFS too. So we want to work on that as well. Also, I guess some of you asked about the homework number 6. It's coming up. So it's tree and heap structure. So binary search tree and heap, some question about that. So right after this video, I'm going to post another video that is going to talk about heap. So if you remember, heap was part of our sorting algorithm on chapter 23. And we said since it's going to use the tree structure, we have to go first talk about the tree structure, and then we come back and talking about heap. So they're both tree structure as well. So I'm going to share the So in 2 days, you're going to see homework 6 coming up. You have a break, but you have your activity to finish. So, okay, can you see my code? Perfect. So as you can see, we did our insert, we did our search, we implemented generic type binary search tree. We'll call it my binary search tree. So now we need to do our delete. So we did just analysis on the delete. So I'm just gonna close some of these. I'll have a lot of things open, like a slides and everything. So we already talked about a different scenario, right? So it's either case 1 or it's case 2. So we first have to start the method delete. Okay. So we have an element and we're trying to delete it. And so first thing you have to do is to make sure this element is actually on the list, right? So the way that we implement our search method is only going to tell us true, false. So it's not going to give us the parent of the elements. And so we have to do exactly the same thing we did already, unfortunately, inside the search. So you can later, fix this code. So our search method, and it's not just going to say true or false. It's actually going to find the father of this. But right now, it's not doing it. So we have to kind of implement this whole thing again. How I'm going to do that is that we're checking if first of all, if we do have something in the list in this tree. So if it's not empty, then I'll start searching for the node that I'm trying to resolve. So I'm going to have the runners. So I need 2 runners. One is going to be the element that I'm trying to find it, the current. And we're both going to start from the root, like what we did. And the other one is going to be the father of it, right? So we're going to have that as well. They're both going to start from the root. And then we're going to go to this while condition, and we keep going. We find that the current is no longer null. That means we find the null that we're looking for. So here we can say, okay, if, and then we're using that compare method that we already discussed, elements. Because you use a comparable interface here. So the node the element that we're looking, if it's equal to the current, that element. If this result of this back as less than or a negative number, we know that this element is smaller, so that's going to be in the left side of our basically node. And so we have to keep going. So the parent now is become the current, and the current become the parent. Okay, just one thing. Sometimes I forget to click on record. Okay, perfect. So just for I have to keep checking, making sure I'm recording everything. So the current is going to become the current dot left, right? So we have to go to the left side now. And if it's not this scenario, my allergy. Then the next scenario is going to be that this is bigger. That means you have to go to the right side. Everything is the same. It's just that I have now to go to the right side. Because this element is going to be bigger than our current node. So now, if it's none of those, then we find it, right? So if it's else, then we're going to basically break. So when we break, we're going to get out of this while loop that we have here, and we're coming right here. And here, that means what happened? I heard a noise. I don't know what was that. When we're here, that means that when I get out of this loop, either the current was null, that means we you know okay, what is that? Oh, somebody joined. Okay, am I in the correct classroom? Okay, I see some of you joining. So hi, I see some of you joining. I'm trying to record this, so it's not like a real live session. But that's okay if you want to hear it, but you're going to get their recording soon. Okay, back to this code. Forgot where it was. Okay, so when we're coming out of this loop, that means that we're finding the current, right? So we are in the current situation, so we find it. And now we have to, what we have here, the current is going to be pointing to the element that we're trying to remove, and we have to check if it's going to be the case 1 now or the case 2. So we find the parents of the current, and we find the current that we're trying to remove it. Now we're either going to be in case 1 or we're going to be in the case 2. So for checking if it's in the case 1, we need to see if the current does have any left children or not. So if the current that left is going to be null, then I know for sure that this is going to be the case 1. So I'm going to write here case 1. So that is no children. So here we have to now do this. So remember, when we don't have any left children, that means if you don't have any left children, that means we are going to be we're in a case 1 as well, and so we have to check if it's it does have any right children. So if it does have a right children, then we're going to tell the parents of it to take care of it. But also another scenario that we had is, what if this current is actually the root? So we did that scenario too. So if the current is, we're going to check that. So if the current is a root, and it doesn't have any left children, that means that the right children of it is become root now. So the root is going to change completely. So here we have to say that now that the current is actually equal to our root, then the root is going to become our current dot right. And we know for sure it doesn't have any left. So it's case 1. Otherwise, if it's not, then it's going to have a father parent. And so it's either going to be in the left side of his father or it's going to be in the right side of his father. And we don't know. And in order to figure that out, we need to do the comparison. So if this element is going to be, we're going to compare it with the parent. We could do also the current. So it's the current and element at this point are the same. It's if this is back as negative value, then we know that this is going to be a left child. So the current dot right is going to be the parent dot left child because this element is going to be smaller than the parent. That means it's going to be the inside. A smaller parent is going to be in the left side of it. Otherwise, it's going to be in the right side of the parent, right? So going to be parent dot right is equal to the current dot right. So that's the case 1. This is the end of the case.